Okay, let's continue. Last time we talked about it for the plane strain problem. Okay, first let's refresh the memories. The character of the geometric shape and for three-dimensional structures, we got one of the directions which is close to infinity, also close to infinity. And so one of the direction, usually we will say that's the axis of the structures. Compared to the dimensions on the cut sections, the dimension along the one of the axial direction close to infinity. Usually we will say that's the z direction. Okay, the z direction is the direction which we have the dimensions close to infinity. And also we have the assumptions about the applied loading boundary conditions, and all these all the things related to the applied force and the boundary conditions. Also the geometric shape on the cut sections. And the basic assumptions is on the xy plane, the geometric shape okay, all these things, they are same. Okay, so for different z, if we cut the cross section on the xy plane, you will find all these things, they are same. And last time I asked one question, and on any cross sections, the points on these cross sections, after we apply loadings to the structures, the displacements of all the points on the cross section, my question is the displacement along the z direction, the w displacement. There are three choices. The w is greater than 0, w is less than 0, or w is equal to 0. And one of you have already answered the questions, and I believe most of you read that the w should be equal to 0. Okay, so the reason you can think about, if we have symmetric structures, okay, if we got a structure, and for this structure it is symmetric about the center line, and the symmetric is not only the geometric shape of the structures, but also the applied loadings, also the boundary conditions. If the structure which is symmetric about the center line, then where the displacement of the points on the center line, we can prove the displacement must be equal to 0. Okay, one of the you can try to understand this, why the points on the symmetric line, the displacement must be equal to 0. You can think if we take a top view, of the structures, and once you take a look from this side, then you can take a look from the other side. You will find no matter you watch the structure from this side or from the upside down, you will find everything you see is the same. Okay, so the structure shape, the applied loading, and the boundary conditions, they are exactly the same, no matter you watch it from this direction or from the opposite direction. Okay, so if everything is the same from both views, then if you say the displacement is to the right, if we have non-zero displacement, for example, if you say the displacement is to the right, then from this view you will say the displacement is to the right also, and you will find it is contradictory. You cannot. It is not possible for a point. It move to the right, also it move to the left. Okay, so the only possibility will be the displacement should be equal to 0. Okay, then let's go back to check the plane strain problems. Based on our simplified assumptions, you can say to the right there are close to infinity. To the left it is also to the close to infinity. Then if you take any cut cross sections, you will find the section you have symmetric. It is although it is based on our simplified assumptions, however you can say it is symmetric about any cut cross sections. And also you can take your view from the opposite direction. You will see exactly the same. And so it is not possible for any point which can have the non-zero displacement, since if you say it is moved to the right, then if you take the opposite view also to the right, then you will have contradictory results from these two views. So it is not possible. Therefore, the displacement on the cross section, no matter which cross sections, the displacement of all the points on the cross section, the displacement along the z direction, it is always equal to 0. It is always equal to 0. Okay, so any point on the xy plane, and the xy plane can be defined on any cross section. Okay, since it is close to infinity, no matter where you cut your cross section, it is still a symmetric plane. So you can use a similar derivation for the displacement on the symmetric line. The displacement must be equal to 0. You can use similar reasons to get all the points on the xy plane. The displacement along the z direction, they must be equal to 0. Okay, so it's time for you to So for the plane strain problems, the geometric shape or the applied loadings, if we like to describe the structures, only a two-dimensional coordinate, the xy coordinates. Okay, only a two-dimensional coordinate system is required to describe what? First, the geometry. The geometry of the structures. But you should remember, we need the xy coordinate system to describe the structure shape of a cut cross section. But remember, you have close to infinity the dimensions along the z directions. It is not a very small thickness like a plane strain problems. Whenever you say you use the plane strain model to consider the problem, the dimensions perpendicular to the cross section, which is assumed to be close to infinity. Okay, we need only the xy coordinates to describe the shape of the structures. Also, we can use the xy coordinates to describe the applied loading. Okay, so for example, if we like to describe a uniformly distributed load applied at the top of the structures, but remember, based on our assumptions, the applied loading is applied not only on these cross sections. For any different z value, if you consider the other cut cross sections, you will see the same distributed load applied at the top of the structures. It is also the basic assumptions. The applied loading, which is exactly the same, no matter which cut cross sections you like to consider. And the third thing is the okay. After we apply loading to the structures, the structure will have the displacement. Remember, no matter which point you are considering in the structure, the W displacement is always equal to 0. So for any point on this cross section, for any point on the cross sections, you can say the only displacements we need to describe, they are the displacements along the x and the y directions. Okay, that's the only two non-zero displacements. They are the displacements along the x and the y. Okay, so usually we consider the plane strain problems. It is two-dimensional problems. It is the same as the plane strain problems. Since for the plane strain problems, also we need only two-dimensional coordinates on the xy plane. But for the plane straits problems, the xy plane, which is the lie on the center layer of a thin plate. And for the plane straits problems, the applied loading, the considered applied load, they are also on the xy plane. The displacements we need to describe, also they are the displacement on the xy. Okay, so that's why we can use only a set of the x and y coordinates to describe the geometry of the structure, the applied loadings, and also when you after you solve the displacement of the structures, you need only this set of the a set of two-dimensional coordinate system to describe all these things. Okay, so that's the typical things for the plane strain problems. The next things we need to consider is the what kind of the strains and the straits we need to consider for the plane strain problems. First, the W is always equal to zeros, no matter which cut cross section, also no matter which point on the you need to consider. Also, you can add also the z direction. So it means that for any point in these structures, the W, they are always equal to zeros. So in this case, the epsilon z since the W is a constant, so if we take the partial derivative of the W to the z, it is also equal to 0. Since the W is always equal to 0, it is a constant. If you take a derivative to a constant, the derivatives must be equal to 0. Okay, also it is not possible to have the shear strain. Since if you got the non-zero shear strain, you still have the displacement, which is so also for the gamma yz all equal to 0. Okay. Okay, if we consider the gamma yz, which is the summations of the partial v to partial z plus partial w to partial y. Since the w, no matter which point considered in the on the cross section, the w is always equal to 0. So this term should be equal to 0. And remember the assumptions. Everything is the same for all the cut cross sections. So the z is not a variable to give you the different v or u. So this term is also equal to 0. So you can say the gamma will be equal to 0. The same thing applied to the gamma zx. You can check the two partial derivatives, and then you can explain why the partial derivatives to get the gamma zx, both terms must be equal to zeros. Okay, so the conclusions will be all these three, they should be equal to 0. Therefore, the only non-zero terms Okay, so for the plane strain problems, the three non-zero strains will be the epsilon x, epsilon y, and the gamma xy. Okay, okay, let's take a print. Okay, so if we have the non-zero strains on the xy plane, then usually we still have the sigma x, sigma y, and gamma xy. Okay, not the gamma xy, tau xy. Okay, since we have the deformation on the xy plane, so usually we have the corresponding strains, sigma x, sigma y, and the tau xy on this plane. And remember, for the plane strains problems, we have the three non-zero strains. But for the plane strains problems, if we got these three non-zero strains, we still have the non-zero epsilon z. If only these three terms they are non-zeros, you will find we have the epsilon z, which is equal to the okay. So if we got these three non-zeros, we got a non-zero epsilon z. But right now we have, for plane strain problems, the epsilon z is always equal to 0. If the epsilon z is always equal to 0, then you can say it is not possible we have only these three, they are non-zero. And the epsilon z will be the okay, remember for the plane strain problems, the sigma z should not be equal to 0. Otherwise, you cannot you cannot counteract the deformations obtained from the Poisson's ratio since we have the strain on the xy plane. Also, it will have the corresponding strain along the z direction. If you like to get the epsilon z always equal to 0, you must have some strains perpendicular to the xy plane. So that's the sigma z. So for the plane strains problems, we have three non-zero strains, but we have four non-zero strains. For the plane strain problems, we have four non-zero strains, include sigma z, but we have only three non-zero strains. Okay, so for the plane strains problems, we have the sigma x, the sigma y, tau xy, and the sigma z. Also, we have the epsilon x, epsilon y, and the gamma xy. But we know the epsilon z is equal to 0. Okay, so along the z directions, the strains is non-zero, but the strains is equal to 0. When we calculate the strain energy, Okay, remember, we can always use this formula to calculate the strain energy for any structural models. So when we calculate the strain energy of the plane strain problems, although we have 4 non-zero terms and only 3 non-zero strains, but you can always neglect this pair, the sigma x and the epsilon, the sigma z and the epsilon z, since we can guarantee the epsilon z is always equal to 0. Therefore, although we have non-zero sigma z, but these two terms, when we multiply them together, for these two terms, they will not contribute to the final strain energy of the structures. So when we consider the plane strain problems, it is the same. We need to consider only the first 3 pairs of the stress and the strain, but we can neglect the last pair. For the plane stress problems, also we consider the first 3 pairs, but for the plane stress problems, it is the sigma z equal to 0, epsilon z is non-zero. But for the plane strain problems, we consider the first 3 pairs, but sigma z is non-zero, epsilon z is equal to 0. Okay, so that's the strains and the stress we need to consider. Okay, so take a screenshot, then I will continue. Okay, let's say what kind of the solution procedure for the plane strain problems. You will find it is over 90% of the solution procedure, they are exactly same as the plane stress problems. And there are only a few points we need to consider them, which is different from the plane stress problems. Okay, so remember, for the plane strain problems, most solution procedure, they are exactly same as the plane stress problem. The first thing is okay, how can we assume the displacement fields for the plane strain problems? Remember, for the plane strain problems, it is still a 2-dimensional problems. So the only non-zero displacements will be the displacements along the x and the y directions. So the displacement functions we need to assume will be the u of xy and the v of xy. Okay, and for the plane stress problems, we could have the non-zero displacement along the z direction. So for the plane stress problems, we have the w of the xy. Since we have the epsilon z, so we could have some non-zero displacements along the z directions. But for the plane strain problems, the w is always equal to 0. However, no matter which problem, the only displacement functions we need to assume they are the u and the v functions. Okay, so we need to describe the displacement on the xy plane. And the description of the structures and the assumptions of the also the assumptions of the displacement functions. We will define the element define the mesh. The mesh will be the include the elements. Okay. Usually we just need to consider the xy plane. So we will use the xy plane to describe the cut cross sections of the plane strain problems. And so on the xy plane, we need to cut the cross section into several elements. And after we define the elements, also we need to define corresponding nodal points. And the number of the nodal points, it could be different. For example, if we use the Lagrange interpolation functions or the Lagrange shape functions, it could be the 4-node element or the 9-node element or the 16-node element. If you use the serendipity shape functions, it could be the 4 nodes, 8 nodes, and the 12 nodes. Okay, no matter which, how many number of the nodal points you like to use for a single element, you need to decide it before you do the analysis. Okay, it depends on the set of the shape functions you like to use for your problems. After you define the elements, also you need to define the nodal points. Okay, the combine of the definition of the elements and the definition of the nodal points, the definition for these two, which is also can be said you are defining the mesh of the problems. And the definition for the elements and the nodal points, or you can say the definition of the mesh, it is also the procedure to describe the geometric shape of the structure. Remember the requirement of the finite element analysis. They are the union of all elements. It must be the entire structure. And the intersection of two neighboring elements, it is only the common boundaries between these two elements. Okay, that's the requirement about the definition of the mesh. And after you define all the elements and all the corresponding nodal points, also you describe the geometry of the structure. Okay, so we need to describe the geometry shapes. Also, we need to describe the displacement functions. And the requirements for the plane stress problems and the requirements for the plane strain problems, they are exactly the same. So the procedure to do the assumptions of the displacement functions and the procedure to describe the geometry of the structures, they are also same. So you can say we have the xy plane, and on this plane you can see the real the so-called the real element, and also you have Cartesian eta plane. The Cartesian eta plane, and on the Cartesian eta plane, you will see the masked element. Okay, so the procedures is the same. We have the real element, and we have the mapped masked element, and for these two elements, they are lying on the two different planes. One is the xy plane, the other one is the Cartesian eta plane. And also we have the two sets of the equations. Okay, we have two sets of the equation. The first two equations, they are the x and y functions, and the user needs to input the x and y coordinates for all the defined nodal points, and also the user needs to tell the program which 4 nodes or which 9 nodes they are connected to this element. So for any considered element, we know all the related xi and yi for this element. So the xi and yi, they are input from the program user. So we know all these informations. Also the phi functions, they are the shape functions or the interpolation functions used for the problem. And we can use the Lagrange interpolation functions to derive all the required phi functions. So all the phi functions, they are also the known functions. Okay, you don't need to guess what kind of. Also the other two equations, u and the v equations. But for the u and the v equations, the ui and the vi, remember, they are the unknown, or they are the assumed values right now. So we don't know the ui and the vi before we solve the simultaneous equations to get the best ui and the vi. Why we say they are the best for the problems, since the solved ui and the vi can give you the minimum total potential energy for the structures. The set of the nodal displacements, which can give you the minimum pi value, they are also the best approximations for these problems. But right now, when we establish the displacement field, when we solve the problems, at the beginning of the solution procedure, the ui and the vi, they are still unknowns. Okay, so remember, the ui and the vi, they are unknowns, but the phi, usually they are same as the phi here. So we know all the phi functions. Okay, so all of these, they are exactly same. Okay, so there is no difference for the plane stress problems, also for the plane strain problems. All the procedures to assume the geometry shape or the displacements, they are exactly the same for these two problems. Okay. So take the print. Okay, and after we assume the displacement functions, then we need to okay, and how do we calculate the B matrix? The B matrix, it depends on the okay. Since the displacement functions, U functions, which is functions of the c and the eta, the coordinates on the c and the eta plane, or for different points on the mass element, we have different displacement functions. So since we know the U functions, although the U functions, they are still functions of the assumed nodal displacements Ui and the Vi, but we can still use the assumed values to calculate the partial derivatives of these two terms. And how do we calculate the partial c to partial x? Usually we solve the J matrix first. Okay, for any element, we have the input xi and yi. Therefore, no matter which point inside the element, we can always calculate the Jacobi matrix. And all these four elements in the Jacobi matrix, they can be calculated in real numbers. So we can always calculate the four elements in the J matrix. And then we can use these four real numbers to calculate the J inverse. The J inverse represents the okay. If we can calculate the J inverse in real numbers, so we can know all these four terms. So what is the partial c to partial x? Usually we just use the calculated J inverse 1, 1. So the first row and the first column element in the J inverse will be the partial c to partial x. Then what will be the partial eta to partial x? And for this element, we can just take the J inverse 2, 1. So the second row and the first column element in the J inverse can give you the partial eta to partial x. And all these will not be changed since the description of the UV functions and the derived phi functions, usually they are exactly the same. And the solution procedure for the epsilon x, epsilon y, and the gamma xy, they are also same. So for both problems, the B matrix we can use the you can say they are same procedure to calculate the B matrix for both problems. And the assumed nodal displacements, they are the displacement vector. It includes all the related nodal displacements for these problems. Okay, so the B matrix is unchanged. And if we can calculate the B matrix, then we need to calculate the D times epsilon, which is equal to the sigma. Okay, But for the plane strain problem, the D matrix, which is different from the plane strain problems. Okay, so the D matrix for the plane strain problems, it is different from the D matrix in the plane strain problem. Since for the epsilon x, and we know this term should be equal to 0. If we take the fourth equations, then we can replace the sigma z by functions of the sigma x and the epsilon y, you can express the sigma z as functions of the sigma x and the sigma y. So usually we will solve the fourth equation first to get the expression for the sigma z. Then replace the expression for the epsilon sigma z from the fourth equation. Then you need to replace the sigma z into the first two equations. So then you can get three sets of the equations. Only the three sets of equations, they are include epsilon x, epsilon y, and the gamma xy on the left side. And also you have the sigma x and sigma y and tau xy on the right side. And that's why usually for these problems we still have a 3x3 matrix. It is a 3x1. It is a 3x1. Okay, so yeah, I think I will take it is the end of the first.